to fire us up. Let's see. Yep, we have started recording. All right, so the first thing we're going to do today is we're going to go over our questions from our last lesson. So everyone do me a favor, grab your textbook and open to page 338. If you have got your assignment, go ahead and get it out. Remember, if you don't make it to the due date, you've got to come to me after school during tutoring to get that assignment done. All right, we're going to go over the answers. So I'm not just going to give you the answers, let you turn them in later. So number one, once everybody gets there, it says approximately how many elements are known today? Anyone think they can answer that question? Kimberly? 115. That's what the book says. Every day people are doing experiments. It's on page 338 and 339. 339 has the questions. 338 has some important notes you're going to want. So if you look up at the chart, this chart actually stops at 103. I've seen charts go all the way up to 120. It depends on what chart. But for the sake of argument, it's a little over 100. A little over 100. All the way up to about 122, I think is the last I've heard. But a lot of those are synthetic elements. They're made in the lab. Right? So 115. Which element has the lightest atoms? This is number 2. Which one has the lightest atoms? What do you think, Elijah? It's the most abundant element in the universe. Hydrogen, exactly. That is number 1 on your periodic table. Okay, number 3. How does the approximate number of atoms in the air in your lungs compare with the number of breaths that exist on our planet? About how many? There was a picture on your book that tells you exactly how, well, roughly how many. We don't know? All right, well, let's go to that page. I'll show you what we're talking about. Grab your book, flip to page, I think it's 327. It is. Look at figure 17.2 on page 327. What does that say? Somebody read that to me. Any volunteers, or am I going to call on somebody? Elijah?
There are many atoms in the normal breath of air, as there are breathfuls of air in the atmosphere of the world.
Now, do y'all understand what that means? A lot of people don't understand that. So it says there are the same number of atoms in one breath in your lungs as there are breaths of air on the planet. So imagine how much air exists in our planet, around our planet. How many breaths do you think that is? It's a lot of air, isn't it? So there are about the same number of atoms in one breath of air as there are breaths of air on the planet. That's a lot. Next up, from where did the heaviest elements originate? Where'd they come from? That's what it's asking. Where do they come from? The heaviest elements. Who's got this one? Nobody has this one? Elijah? All right, Chris. That's pretty close. That's pretty close. Look at the bottom of page 325. It says right here, the heavier, naturally formed atoms that we find around us were manufactured by fusion reactions in hot, high-pressure cauldrons deep within the stars. So what that really tells us is that all of these heavier elements, anything that's really far down on the bottom of your chart, comes from stars. Stars take gases and matter in the universe and they condense them down. And those reactions are where the fire comes from the stars. That's what fuels the stars. So that's where all of our heavy elements come from. So the heavier elements, like the metals that are found in your body, some of the heavier things like sulfur, it may be, definitely anything towards the bottom, all those come from stars. So some of the things, like one of my favorite people in science is Carl Sagan. And Carl Sagan says that we are all made of stardust. And it's true. All of the material in your body at some point exploded out of a star. And sooner or later you get human beings. It's pretty wild if you ask me. Next up, number 5. says, how do the sizes of atoms compare with the wavelengths of visible light? So we're comparing the size of an atom to the visible wave of light. What's the comparison? Didn't get this one? So wavelengths of light. When light travels, it doesn't go in a straight line like we really think. It actually does this. Because light operates as a wave. Right? So if I were to look at an atom is really tiny. So an atom is actually smaller than the wavelength of light. Which is why we can't see atoms. They're so small that the light can't even bounce off of them. Everything that you see in the world, light hits it, bounces off of it, and comes into your eyes. And your eyes take that signal, and we build this vision of our world. So if the light is so big compared to the atom that it actually goes around the atom, you can't see the atom. Because you need the light to strike the atom and come back to your eyes. If it doesn't, you don't see it. So atoms are actually smaller than the wavelength of light, which is why we can't see it. Number 6, how does the age of most atoms compare with the age of our solar system? So that's Mercury, Venus, Earth, Mars. What do you think, Chris? Exactly. So you've heard of the Big Bang, right? Scientists believe that all matter in the universe was condensed into one point, and at some point in known history, those atoms exploded out into space. And then billions of years, like 14 billion years later, we have planets. You didn't get your paper? That's let's see here. I think I got you right here. There you are, Dre. There you go, sir. There you go. Cover up. And you're safe. All right. So atoms are actually older than our solar system. We can't really say for sure that they're older than our universe, because as far as we know, they all originated at the same time. Right? But our solar system is not the newest solar system. It's not the oldest solar system. So the atoms that make us up and make up Earth and everything in our solar system are actually older than our solar system. That's in right now. I'm talking to your principal about whether or not I'm going to let you guys turn stuff in late, because it doesn't make sense for you to turn in an assignment that I'm giving you the answers to right now.
But we already did it, right?
Yeah, that's when I graded it. That's why I gave you back your graded paper. And now I'm going over it, and if you just wait until I go over it to write the answers down, that's not doing work. It's just writing down notes. You're turning in notes, not an assignment. Right? All right, so atoms are actually older than our solar system. Next up, number 7. Number 7 says, what is meant by the statement that you don't own the atoms that make up your body? Well, I mean, when I die, sooner or later, everything that makes me me is going to break down and go into the environment. So, let's see what Quinn's got to say.
You simply their present caretaker.
That's what the book says. Now, what is a caretaker? Y'all know what that is?
Take care of that person.
How many of y'all got a family member who's sick, a lot, you got to take care of, right? So, Quinn, you're the caretaker for that family member, right? You're responsible to help them out, right? So we are all caretakers of the atoms in our body right now. I have got trillions upon trillions of atoms in me right now that I'm sort of the boss of, if you want to call it that. But those atoms, I could have some Einstein right here. I could have Joan of Arc right here. I could have Gilgamesh right over here. All of these big things and big people and things in history, those atoms, they get recycled. So you don't own any of those. When I die, a million years later, some other person is going to have some of my atoms in them.
Wait,
So
you die what?
when we die, okay, how many of y'all like The Lion King? Love The Lion King, right? So there's this point where Simba's dad is talking to Simba, and they're looking over the kingdom, and he talks about the circle of life, right? So grass grows from the sun, gazelle eats the grass, lion eats the gazelle, lion becomes the grass. Y'all remember that? That's the circle, right? So the atoms that make up the grass get eaten by the gazelle. They become part of the gazelle. The gazelle gets eaten by the lion. Those atoms become the lion. Then the lion dies, decomposes into the earth, and then that becomes the grass. So your atoms don't really belong to you. They get recycled. All right, number 8. Number 8 says, what causes dust particles to move with Brownian motion? First of all, what is Brownian motion? It's kind of a hard concept. Now, I don't want you guys to focus too much on this because this isn't going to be on your test. But just so you know what it is, imagine you're in a plane flying up in the air and you look down into Stratford's football field. Are you going to be able to pick out the individual people? Probably not. You can kind of tell they're there, but you're not sure. What if I took 50 of you and we put like a 6-foot bright red beach ball in your hands and you guys bounce the beach ball around like this? Would you be able to see that? Yeah. That's pretty much what Brownian motion is. All of the atoms around larger objects vibrate, which causes those larger objects to vibrate. And scientists can detect those vibrations. We can see that, but we can't see the individual atoms. Vince, do me a favor, man. Get that head up. I need you to join us, okay? So Brownian motion is the motion caused by vibrating particles. And we can see it when there's a bunch of little particles moving a bigger particle, like dust. We don't think of dust being very big, but compared to an atom, it's huge. All right, number 9. Invisible atoms cannot be seen with visible light. Yet there is an image of individual atoms on diagram 17.4 in your book. How does that work? What's going on? I just talked how light is, the wavelength of light's too big to see the atom. How can we see atoms? This is a tough one. So is visible light the only kind of light? No. It's all sorts of wavelengths of light. And you can do other things. Like we have this amazing technology called electron scanning microscopes. They actually fire electrons at a surface or an object. And then they time how long it takes for those electrons to come back. And we can build an image of something using electrons, just like we do light. And that's how they're able to see light, because electrons are super tiny. They're even smaller than atoms. They are the smallest subatomic particle that we're going to discuss. So if we fire enough of those and build an image of something, we can use the electrons to see things. And that's what we've developed. Electron scanning microscopes. They let us see really, really tiny things. Elijah, come on, man, get that head up. Thank you, sir. All right, last one, number 10. What is the purpose of a model in science? This one was tough. It doesn't explain it very well in your book. Well, there's a couple of things. One, a model could be, let me pan over here. This is something I learned a lot about when I took organic chemistry. This is a molecular model. This tells me how a molecule is shaped. This is actually benzene. So this is a model of a molecule. I can't see molecules because they're too small, but I can see this. So this lets me understand something that is probably too small or complex. Another thing is weather models. We use weather models to predict the weather. Y'all ever wondered how the meteorologist says, well, there's going to be rain in 3 days? Y'all ever wondered how that happens? We have simulations that we run on computers. We take data like the barometric pressure, temperature, winds, humidity, and we combine all that into a weather model, a simulation, to predict weather. So models let us make predictions, and they also help us understand things that are hard to understand the way they normally are. All right? So now, let's get ready for today's lesson. Now that we reviewed last lesson, today our standard is 3237.5.1. It is Identify the parts of a atom, or an atom. Don't let your English teacher hear me say that. You know, I have my head. So the parts of an atom. Can you guys give me one part of an atom? Who can tell me one part of an atom? Electron, there's one. Neutron and a proton. That's it. Those are the three things we're covering today. Protons, neutrons, and electrons. So let's take down some important notes. I've got a couple of cool videos for us to watch today, and then we have one assignment. If we get through this quickly, you will have time to finish your assignment today. I had several students last class finished it because they were on point and they were doing what they needed to do, and we got it done. So let's start off with a little bit of notes. Everybody get your notebooks out. Let's write this down. Parts of an atom. I want you to put that at the top. Parts of an atom. Nick, get your paper out. Let's go. Freedasia, do you have paper? Come get some right here. You got a pencil? Do you have a pencil? No? Do you have a phone you can trade for it? I'll give you a pencil if you got something to trade for it. You're going to want the book. Keep the book. There's a periodic table in your book. I've got one you can take home for your assignment, but I want you to have that book with you. No, I can't give you the book. We have a classroom set. But there's a digital copy on Blackboard. All you got to do is get on. This chapter's on there. Yeah. Huh? We ready? Yeah. All right. So, parts of an atom at the top of your page. First part we're going to talk about, number one, is the proton. Now, can anyone tell me anything about a proton? No? Oh, man, that lesson that we read, we were supposed to read that? Ooh, we struggle, right? All right. What about the charge of a proton? Does anyone know what the charge? Take your hood off, man. I'm going to ask you nicely one more time. Please take your hood off. Yes, you. Yes, you. Please take the hood off. Take the hood. Just chill. Just follow the dress code. Kendrick, just relax. Are you okay? All right. So protons are positively charged. P and P. Proton, positive. Positively charged. So I put a plus. They are positively charged. Can y'all tell me where the protons are found in an atom? Vince. Last time I'm asking you, sir, get your head up. If I have to ask you again, you lose your seat. Where are they at in the atom? All right. What do we call the center part of an atom? In the center. What was that? Nucleus. That's exactly right. They are found in the center of the atom, and that is called the nucleus. Just like in cells, cells have a central part. The brain of the cell is the nucleus. Atoms also have a central part, and it is called the nucleus as well. You can find the protons there. Center of atom and nucleus. One more important thing that we need to know is that protons give us the atomic number. And we'll learn what atomic number is here in a second. So these are the three things you need to know about protons. They are positively charged. They are located in the center of the atom that we call the nucleus. And they give us the atomic number. And that's going to be stuff that comes from this chart up here in just a bit. I'll give everybody just a little bit longer to write that down. Elijah, you want to be writing these notes down. Kendrick, you want to be writing these notes down. I gave you an option. You decided not to take it. You got to come to class prepared. All right, next up. After the protons, we are going to learn about the neutrons. Someone want to take a guess where the neutrons are located? Shout in the dark. Shout something out. Where in the atom is the neutron located? It's in the nucleus. So same thing as the last one. Center. Oh, I skipped one. center of the atom, and that is the nucleus. All right. What about the charge? I was going to start with the charge, but I messed up. Charge is not negative. A lot of people think neutral negative, or neutron negative. It's actually a neutral charge. It has no charge. So when you see neutron, I want you to think neutral. All right? So they have no charge. We call that neutral. So neutrons don't give us any positive or negative for the atom. All they actually do is give us mass. And another thing they do is they keep the protons together. Now, can y'all remember from our last unit? Positives do what, similar charges do what, and dissimilar charges do what? Like repels, and the other ones attract, right? Like repels and opposites attract. So if I've got a bunch of protons all packed together in the nucleus, what do they want to do? They want to get free. So it's like you got a bunch of kids that are just running around crazy. The neutrons come in and get those kids in a huddle, put them in a headlock, say, you're not going anywhere. The neutrons are kind of like the glue that keep the protons from flying out of the nucleus. So they are in the center in the nucleus. They have no charge, neutron, neutral, and they help us with mass. Give atoms mass. And that's going to be important when we get to part of our assignment for today. So those are our 3 parts. What's left? Electrons, exactly. So I'm going to give you all just a little bit longer to write this down. Proton, positively charged, in the nucleus, give us the atomic number. Neutrons are neutrally charged, no charge at all. They are in the center of the atom as well, and they help give the atom mass. All right. Now let's go to the next part. Talking about the 3rd subatomic particle, the electron. Sometimes you'll see them put E negative like that. So let's start correctly this time with the charge. What's the charge on an electron? We learned this last unit. Well, if a proton is positive and a neutron is neutral, what do you think the electron is? It's definitely not what? You don't think? It is negative. So electrons are negatively charged. Negative. They are located where? On the outside. So when you guys see atoms, when you see models of atoms, a lot of the times you see this. Right? Y'all have seen this before, right? Your boy Jimmy Neutron? Right? So this is the nucleus. These out here are the electrons. So they are on the outside. They are in orbitals or shells outside of the nucleus. So let's write that down in our location. They are outside of the nucleus. You can if you want. I mean, you should have drawn those already with your last assignment. Second dot is outside of the nucleus. Think of shells. Remember our buddy Bohr? Niels Bohr, who discovered the shells, the stages of electrons? What about what electrons do? They don't give any mass, so they are too small for mass. They actually give a little bit of mass, which is why you get the decimal points on the periodic table. All that left over, protons and neutrons are all solid numbers. But electrons give us that itty-bitty bit. They're actually a lot smaller even than the protons and neutrons. They're negatively charged. They're located on the outside of the nucleus in the shells or orbitals, and they are too small for mass. So y'all ready for some video? Y'all look like y'all need something a little up. Y'all ready? All right, let me pause this.